Hello there, welcome to the channel and welcome to the fourth video of the machine learning problem solving series. So far we have learned how neural networks generate outputs using activations and softmax. But here's the big question. How does the model actually know it made a mistake? How does AI learn from being wrong? That's exactly what we are going to understand today with one of the most important concepts in deep learning, which is cross-entropy loss. This is the loss function used behind image classification, language models, recommendation systems, and even model LLMs. By the end of this video, you'll understand what cross-entropy really means, why it works so well with softmax, and why almost every classification model depends on it. And also, we will be implementing cross-entropy loss in Python code. So let's get started. Before we understand cross-entropy, we need a quick recap of softmax from the previous video. A neural network first outputs raw scores, which is called logits, something like 2.1, 0.3, and negative 1.2. These are not probabilities yet, so softmax converts them into probabilities. For example, for here you can see the probability of input being cat is 76%, of being dog is 17%, and of being rabbit is 7%. Now, the model can express its confidence, but we still need a way to answer one important question. Were these probabilities good or bad? That measurement is called cross-entropy loss. Now, what is cross-entropy loss? Cross-entropy is basically a way to measure the difference between what the model predicted and what the correct answer actually was. In machine learning, P represents the true labels and Q represents the model predictions. Suppose the correct class is dog. The true labels becomes 0, 1, 0, and the model predicts 0.1, 0.7, 0.2. Cross entropy focuses only on the probability assigned to the correct class. So the loss becomes negative log of 0.7. As you can see here, the higher the confidence for the correct class, the lower the loss. So the formula here is HPQ is equal to negative summation of Px into log of Qx. Now, why negative log? Now here's the interesting part. Why do we use the log? Because it creates the perfect punishment curve. If the model predicts the correct answer with very high confidence, the loss becomes almost zero, as you can see. But if the model gives a very low probability to the correct answer, the loss becomes huge. And that's exactly what we want. Confidently wrong predictions should be punished heavily. That's why the negative log function works so well. And here we can see the formula we have used is y is equal to negative of log p. Now let's look at the complete formula. Don't worry, it looks more complicated than it actually is. Now in the given formula you can see n is the batch size, y is the true label, and y hat is the predicted probability. But because the labels are one hot encoded, almost every term becomes zero. Only the correct class survives. So the formula simplifies beautifully into this. This is the one formula you should always remember, which is this. Now, we'll be saying there are two major versions of cross entropy. Binary cross entropy, which is used for two class problems like spam detection, fraud detection, and sentiment analysis. And there is categorical cross entropy, which is used for multi-class classification like image recognition, NLP token prediction, and object classification. Binary cross entropy works well with sigmoid. Categorical cross entropy works with softmax. So these are the two different formula for two different kinds of cross entropy. Now, why not mean squared error? So you might ask, why don't we just use mean squared error? The problem is gradients. With sigmoid plus mean squared error, gradients can become extremely tiny when the model is confidently wrong. That slows learning dramatically. Cross entropy fixes this problem. When combined with Softmax, the gradient simplifies into something elegant: prediction minus truth. So, as you can see, this is the formula that we have used here in cross entropy. So, telling simply, this creates stable learning and much faster convergence. Now let's implement this in Python code. Now let's begin with the implementation of cross-entropy loss. So we'll be implementing both kinds of cross-entropy, which is binary and categorical one. Let's begin with the binary cross-entropy loss. As you can see, the formula for binary cross-entropy loss is like this. So what we are given as function parameters here is yTrue, which is an n-dimensional array, and ypred, which is also an n-dimensional array. So what we are going to do is we are going to detect how much is the predictions deviated from the true values. Let's begin. So first we define epsilon. So for this question we would be taking it as 10 to the power minus 7. Epsilon must be very small so that it doesn't hamper our original values. And then we will be clipping all the prediction values between the epsilon and the original values. So as you can see, we'll be using here clip function in numpy module. Epsilon comma 1 minus epsilon. So yeah, we have clipped all values so that we don't give values lesser than 0. What happens is log can't be calculated for the negative values. That is why we have used clipping and epsilon here. For calculating the loss, we will be using this formula, which is minus np.mean. Now why mean? As you can see, this formula looks like a mean because you are summing up the values like this and then dividing by the total samples in your array. So this is like calculating mean. Now we have to just write what's inside it. And now just following the formula, which is yTrue times np.log of ypred plus 1 minus yTrue times np.log of 1 minus ypred. So yeah, this is our binary cross entropy loss calculated. Now, since the question demands we have to round it to 4 decimal places, we will be rounding it to 4 decimal places by using np.round. np.round loss and rounding it to 4. Now let's implement the categorical cross entropy. As you can see, the formula for categorical cross entropy is like this. Binary cross entropy is used for 2 classes and categorical cross entropy is used for multiple classes. Let's begin. Now here also we will be defining epsilon. What we have could done is we could have defined epsilon globally so that we could have used it in both the functions. But since we have used it locally, so we'll also be defining it here locally. Epsilon is equal to 10 to the power minus 7, and then we will be calculating predictions. So here predictions are clipped between epsilon and the original values like before only. There's no difference. Then we'll be calculating loss using the formula np.mean np.sum yTrue times np.log ypred, and then x is equal to 1. Now we'll be returning the loss, and this loss would also be rounded to 4 decimal places. So yeah, this should work. As you can see, our initial test cases have passed. Let's now submit it. And as you can see, the problem is implemented successfully. Here are some common beginner mistakes. Number 1, applying softmax before cross-entropy loss. Number 2, computing log of 0 without epsilon. Number 3, using cross-entropy for regression problems. Number 4, ignoring class imbalance. And number 5, no label smoothing, which can make models overly confident. Now let's summarize what we learned. Cross-entropy measures how good the predicted probabilities are. It heavily penalizes confident wrong predictions. For one-hot labels, it simplifies into negative log probability of the correct class. And when combined with softmax, it produces stable gradients that train neural networks efficiently. This is one of the core building blocks behind modern AI systems. If this video helped you understand cross-entropy loss, make sure you like this video and subscribe to the channel. And in the next video of the machine learning problem solving series, we'll move from loss functions to actual prediction models by building linear regression from scratch. Thanks for watching, and I'll see you in the next one.